Hello. This time, we're going to spend some time talking a little bit more about the equilibrium on solutions of weak acids and bases. And we'll do this on this chapter, and we call it chapter 17. In a different textbook, it may be chapter 16. So use as a reference the topic we are discussing rather than the chapter number. I use the chapter number so you can follow and keep track of the sequence of the chapters, but pay attention to the nomenclature of the chapters. So we'll do the equilibrium in solutions of weak acids, and we are going to break this chapter in two parts, chapter 17a and chapter 17b, that will cover equilibrium of insoluble salts. Again, this chapter 17 is still acids and bases chapter, but dedicated especially to weak acids and weak bases. Here I wrote a summary of what we did last time, so I'm going to go very quick on this first slide because this is just a repetition of what we did last time. You can use this for reviewing. Last time we talked about acid ionization constant. I showed you how to do it. I gave you an example of what we can do. Also, we can become familiar with the pKa, which is just a negative log of the equilibrium constant Ka. Remember, I told you last time when we were mentioning the pH, that the pH concept can be applied on different situations to produce a logarithmic relationship, a logarithmic scale. So as you can recall, I gave you the example that if pH equals negative log of concentration of H plus, we can use the same scaling, and we can virtually find the px, where x is can represent one measurement, and that will be equals to negative log of x. That's why we were able to use POH. So POH will be negative log of concentration of OH minus. And it's going to be very useful to find the pKa for the weak acids. And that will be negative log of Ka, of the acid. Similarly, we can find the pKb for weak bases, and you will see that later. That will be negative log of Kb. Why do we want to do this? Just to simplify the numbers. Remember, for example, concentration of H plus, if we have concentration of H plus equals 1.0 times 10 to the negative 7, which is 0.1234567. Very small number. So instead of writing this very small number or writing this scientific notation, it's more convenient to use pH. To give information about the solution, about the hydrogen potential of the solution, which is the pH. So it's more convenient to say, okay, the pH of the solution is just 7, because negative log of this number is 7. Isn't that easier to work with that number, 7? It will make more sense when we draw a scale of pH, pH scale from 0 to 14, and 7 is somewhere here for neutral. So it gives you a better idea of the hydrogen potential of any solution, and we call that a pH. But remember again, I mentioned it before, the pH scale is a logarithmic scale. It's not proportional. Meaning, if the pH of a solution is 7, and the pH goes up to 8, it's not going just one unit in the pH scale. It will represent an increment on the concentration of H plus, in this case going down, because it's going to be less concentration of H plus, but the difference is exponential. So it's 10,000, it's 1,000, it's a tenth of difference, because the new concentration here for pH 8 is going to be 1.0 times 10 to the negative 8. So it's 1/10 of difference compared to 1 times 1.0 times 10 to the negative 7. So we have to be careful with the scale. The scale is logarithmic. So that means the concentration H plus on pH 7 is 10 times bigger than the concentration of H plus for a solution that has pH 8, and so on and so forth. The concentration of H plus on a solution with pH 6 is 10 times bigger than the concentration of H plus on a solution that has pH 7. So be aware of that. So this produces, when we use pH, px, pOH, pKa, or pKb, we're talking about a logarithmic scale used to simplify writing these numbers and to create a more visual scale. Similar with the Kas. Like, for example, we are familiar, let me see if I have the next one example. No, all right. I can give you one here. For example, if we're talking about the acetic acid, and for the acetic acid, the equation will be like this. In equilibrium, remember this is a weak acid, H3O plus aqueous plus the acetate ion. And we know the Ka of this acid. The Ka of this acid is 1.8 times 10 to the negative 5. So sometimes it's more convenient if we use pKa instead. So on the table, sometimes you won't find pKa's or only Ka's, or sometimes you will find only pKa's, no Ka's, to show the extent of that equilibrium. So what is the pKa of acetic acid? Knowing that the Ka is 1.8 times 10 to the negative 5. Simply just take negative log of that number, 1.8 times 10 to the negative 5. How do you do that in the calculator? So let me show you. In our scientific calculator, we just need to make sure you have the function. All scientific calculators have the function. This is log, and this is the natural log. We are using for pH is log base 10. And so we write the number, which is 1.8 times 10 to the negative 5. And we want to take the negative log of that. But there's no negative log. It's only log of that. So you add the negative after you do the log. So let's just do log of that number, and that will be negative 4.74. But since the equation says negative log, then negative times negative, it cancels that. So the purpose of the negative in the formula is just to convert your result in a positive number. So the pKa for the acid is going to be 4.74. Usually we work with 3 significant figures. So we can leave it 4.74. And that will be the answer. That will be 4.74. So you see, it's more convenient sometimes saying, okay, pKa is 4.74. Or if the problem gives you only pKa, but during the process you need to know the actual value of the Ka, well, you can convert this into Ka. How? Do the anti-log of this. So that will be Ka. Ka will be 10 to the negative pKa. And you will get back your number. So either way, so a lot of times, this is what we need to do. Use this, or sometimes you need both numbers. You will see applications of this later on. Similar, you can do the same thing, same idea with KBs. So you have the KB. Sometimes it's more convenient to talk about pKbs. So you do the same treatment with your numbers. All right, this is just to refresh memory about Kas. Another thing you have to be careful is that when comparing Kas for the weak acids, remember, if this goes up, the negative exponent of the weak acid, of the Ka of the weak acid, that means the higher this number, this exponent, which is negative, that means the acid is weaker. And the pKa goes up. So when the pKa goes up, don't think it's getting stronger. No, it's getting weaker. So you have to be careful with that. That goes opposite. So a small pKa means large value of Ka. And large fraction of the acid molecule ionized, that means makes stronger. So if the pKa goes down, the number, that means the acid becomes stronger. If the pKa number goes up, that means the acid is becoming weaker. So similar with the acid, with the bases, we did already. We don't need to repeat this. We did this already. I explained the relationship Ka and Kb for the conjugated acids and bases. How to show you actually a couple problems using this formula. So you can watch the previous video to see that. This is, we did already. I think I solved this problem already in the previous one. So you can go back and check. Here is the list of weak acids and weak bases compared to relative comparison between them. And also how the strength of these ions can give us clue whether or not the ion is going to react with water to produce a secondary reaction, changing the pH of that solution. We did that also on the previous video. But I put it here so you can stop and read. It will benefit if you stop and read, if you can go back to refresh the memory of what we did. All right, so remember we did this last time. So I put more examples here so you can practice. That was done on the previous video also. Same thing, I think I solved this on the previous video. So you can go back there to find the pH of this salt. And that was there. We did percent ionization already for weak acids and bases. This is another example you can practice with. So I put in here a lot of information we did already on the previous video. So we can go ahead. Bases, we did already weak bases and show you how to do this. Sometimes we get we have to solve it using the quadratic equation, but sometimes we can just do an approximation. You have to prove that your approximation is right. That way, a lot of times we can go around the quadratic equation. Here is the analysis I showed you before to figure the nature of the solid, the nature of the salt, the cations, the anions, and to find the pH under different circumstances. So I put this one because I think this summarizes also what we did last time, and that will help you to remember how it works. We did problems like this. The sample problems are done on the previous video, so go back check how we solve these problems, and then you can solve this without cheating. Here is the answer, but don't cheat. Just do it yourself. Go back, do the exercise. Sometimes you need to struggle a little bit to make our brain work better. So once you solve it, then you come and compare here. Again, don't cheat. The answer is here. Try yourself first and then come back and see. Compare the same thing with this. The answers are there. I show the procedures, how to do it, step by step. But this is just repetition of the same problems we did before. So you try with those. Let me see. Do you have answer? The answer is here for this one. This one also. All of them that were solved already. You find a different way to do it. You can publish it. And I hope I can see your inputs in the Blackboard discussion. We have a forum there to put the questions you are trying. You find a different interesting problem and you can solve it, put it there so everybody can make inputs on how to solve the problems. We like to see different approaches to solve a problem. If you have, you're struggling solving one problem, same thing, publish it there, Blackboard discussion, and we'll solve it. That's how we improve our knowledge and our skills. I explained this already. So pretty much we did already. That was the previous example, same thing here. Okay, this is new. This is what I wanted to arrive. So buffer solutions. And here we are going to apply all what we learned about weak acids and weak bases. This is a really interesting topic. Has a wonderful application, especially in biology. Chemistry too, but more applications on biology in general. So what is a buffer solution? A buffer solution is actually a mixture, a homogeneous mixture. So a buffer solution is a solution that contains, let me write this because this is the basic definition of buffer solution, and it needs to be very clear. If you understand the definition, you will understand what is a buffer and how the buffer works. So let's put it here. A buffer in chemistry, we're talking about definition of buffer in chemistry. Buffer may have different meanings or applications in different areas. So the buffer in chemistry is a solution. That's your first count. Is a solution. That means it's a mixture. It's a homogeneous mixture. Remember, solutions are homogeneous mixtures. And that solution contains, or that solution is made of two parts. First, must contain a weak acid. Or a weak base. So right now, we just realized that there are two types of buffers, a acidic buffer or a basic buffer. So what is an acidic buffer? Well, any buffer that works with pH less than 7. And any buffer that works with the pH bigger than 7, that will be a basic. So again, a buffer is a solution that contains a weak acid. And also contains the salt of that weak acid. Not any salt. Has to be the salt of that weak acid. And how do we call the salt of the weak acid? Do you remember? I mentioned it before. That will be the conjugate base of the weak acid. So this is a requirement in order to achieve the properties of a buffer solution. That's how you make a buffer. You need a weak acid and you need a salt of the weak acid. In other words, you need the conjugate base of the weak acid. You need to add this independently. Remember, the weak acid, when you add the weak acid into the water, the weak acid is going to form some conjugate base. It's going to form a conjugate base. However, you need to add extra from an external source. And that's how you make it. And that will be a acidic buffer. You want to do the basic buffer, we do the same thing. But in that case, you are going to use a weak base. And what is the second component of your basic buffer? Yes, the salt of the weak base. The salt of your weak base, the weak base you are making here, find what is the salt of this and add extra from a different source. So you have to add two components there to prepare the solution. And what is the salt of the weak base? Is the conjugate acid of that weak base. And that's a buffer. And why do we want to do this? What is the point? The way these two are going to work. So that once you prepare that solution has the ability, it's a property, to resist changes in pH upon the addition of small amounts of acids or bases. And that's the main purpose of making buffer. For instance, let's say we have here we prepare a buffer. So you are working, let's say you are working in the biology lab and you're working with special cells. As you know, these special cells you are working with needs a very narrow pH to survive. So the media that you are going to use to grow your cells needs a special pH. So the protocol says grow your cells in a pH, let's say maybe I'm just going to throw a number there. 6.2. Sorry, this is pH. pH equals 6.2. It's very specific, pH. So you need to prepare a media with the pH. What's going to happen with your cells if the pH is not 6.2? Let's say the pH is bigger than 6.2, let's say 6.5 or even 7, or what happens when the pH is less than 6.2? Well, you will kill the bacteria or the cells, wherever they are. Because it happens that these cells requires a very narrow pH media to survive. The optimum, that is called the optimum pH. Some cells, some bacteria can survive in different, in a wide range of pHs. There are even bacteria that lives in pH around 1 and 2. Very acidic pH, and they can survive under this extreme pH condition. But others will not. And you need to make this buffer pH 6.2. And that solution must have the ability to resist the change of pH if some acid comes in contact to the solution or some base comes in contact. So let's say you have this container in your lab and somebody by mistake add few drops or few mLs of strong acid, let's say HCl. Since you have a buffer, your buffer should be able to resist, to adjust, so the pH of the solution will not change, even if you add small amounts of strong acid. If you add small amounts of strong acid in just pure water, no buffer, the pH of this is going to go dramatically down. From 7, it's going to go, depending on the amount, but it's going to go at least 2, pH 2. That will kill bacteria that are not adapted to the pH. That's in pure water. Let's write just water. Luckily, you have a buffer. So no harm will be done on your cells because the buffer will make the adjustments to keep the pH of very close to that. It can tolerate changes in this order of the magnitude, but not big changes. At least that you throw here a liter of hydrochloric acid, that will destroy your acid. Similar, if by mistake you add a solution of a strong base, that will, if you add the strong base in just water, the pH will go up and will kill whatever you had there. Luckily, again, you had a buffer, and that buffer has the ability to resist pH changes. So it will make adjustment by itself to keep the pH. Upon the addition of small amounts of acids or bases. Small amounts, that's key also. You will not tolerate addition of any amount, again, only small amounts. All right, so that's a buffer. So let's work in different scenarios how to make buffers and some problems. Here it's important that you realize that we can make any buffer, any pH as needed. So if somebody asks you prepare a buffer with pH 5.5, you can make it. So your buffer will stay at 5.5 pH. I'll show you how to prepare this solution. The key there is to select the right weak acid. You select the weak acid that falls into the range that has a pKa within the range of the desired pH. Same thing here for the weak bases. So let's say you want to prepare a buffer with pH 8.4. The key is to choose the right weak base that has a pKb close to the pH you want. So you see how important it is, because from now on we are going to use the pKa's and pKb's. That's why we learned before the meaning of that. So this is how it works. So the buffer, let's assume we have a buffer here. Your buffer solution contains or has two components. One, the weak acid, and two, the salt. So look, the weak acid is going to be HA, that represents any weak acid. Right? And the weak acid is made of the proton, that is the acidic proton, and an ion, which is the salt, or which is the conjugate base of the acid. And also the one. I have to insist many times about the composition of the buffer. Again, your buffer solution must have these two components, the weak acid and the salt of the weak acid, which is that one, from a different source. And therefore we have two equations. The first equation for the equation of ionization of the weak acid, which is the one that we already know. The weak acid here. If we add some base to the solution, what's going to happen? How this weak acid is going to work to counterattack the aggression made by the addition of OH minus to prevent the change of pH of the buffer after you add this undecided extra base to the buffer, where the acid will come right away and we'll use protons to neutralize the OH minus to make water. That way it neutralizes the OH minus. So you see, this is the molecular form of the weak acid. Remember, the weak acids are weak. And why we call them weak? This is your weak acid. Aqueous reacts with water, liquid, to form an equilibrium with H3O plus AC minus. Oh, I was using acetate. Let's use a generic. Doesn't need to be acetate. Any salt. A minus, aqueous. This is the initiation of the weak acid. So you add that into your solution, and notice that the weak acid is making the hydrogen ions, and it makes the salt. And this salt comes from here. But remember about the equilibrium, and remember that this is a weak acid, and we know this weak acid has a very small Kas. Kas are very small. Therefore, the pKa's are big, Ka's are very small, pKa's are big. That is for the weak acid. In other words, for any weak acid, the main reaction always goes to the left. I explained that last time also. This is a strong hydrogen ion, and we have a strong conjugate base, and this plus or minus, that you realize right away they are going to react right away to push the equilibrium to the left. So at the equilibrium, mostly everything is going to be molecular acid. Very little dissociated. And you know the extent of this dissociation just by looking at the numbers. So on your buffer, this one will react with, this is a strong base, and this will take all the hydrogens it needs, all of them. If you add 3 ions of this on your solution by mistake, you buffer, you have your buffer there. So this reaction is happening there. And this reaction is also happening there. Reaction 1 and 2. So you have that. You have HA, your weak acid, and you have A minus. From 2 different sources. So you add acid, HA, with the amount, the right amount. Well, you'll show you how to calculate how much of the weak acid you need to add. And you need to add a salt, a different source, containing your acetate, or not necessarily acetate, but your conjugate base. Any salt, crystal, or a solution containing that. And I'll show you how to do, how to calculate how much of this, how much of that you will need to produce a specific pH. But your solution has this molecular form because mostly everything is molecular for that weak acid. If you add extra OH minus, that will take all your hydrogens from here, forming acetate ion. Let me put a different color. Acetate ions that comes from that reaction, and water. But remember, there are acetate, you already have acetate ions there. What for? Just in case that somebody else comes and by mistake add some acid to that. So let's see what happens with the addition of some acid. Who's going to help to counterattack the extra addition of H plus? Well, you have plenty of acetate here, this one, from that source. Because again, and this is a different scenario, this acetate is producing, this weak acid is producing some conjugate base, some salt, but very little, because it's a weak. Very little of this is present there, coming from here. So very little of this green A minus coming from here. That's why you need to add extra from different source, like actual salt, and add it there. And that is the blue one, blue A minus. So when somebody adds H plus to the solution, is the A minus who will come to the front line to take the extra H plus that has been added to form HA. So in this case, it's going to save your solution when somebody adds extra acid. And this is the reaction for that process. So that's why you have the two components. One will help to save your solution from extra additions of OH. This one. The molecular acid. And the salt will help in case somebody adds acid. And that will keep, both of them will keep the solution in a good pH balance. As a result, no big changes on the pH because you have to save yours there. That's a buffer solution. You see how important are those, especially in biology applications? So, let's do a real thing. Check this problem. It says, what is the pH of a buffer made by adding 0.10 molar ammonia and 0.11 moles ammonium chloride to 2.0 liters of solution? The Kb for the ammonia is given, and we already know that, right? Kb of the ammonia is 1.8 times 10 to the negative 5. Okay, let's do analysis. I like to always do the critical thinking on every problem, get the maximum information, and I spend that time so you can do the, you can understand the actual problem and how to approach it, and then you apply the same concepts to solve different problems. We say it's a buffer. Let's see if that fulfills the requirements of the buffer. So we say the buffer must have two things. In this case, what kind of buffer is this? Acidic or basic? What would you say? I will say it's a basic. Why? How do we know? Because they are using ammonia, and we know ammonia is a base. It's a weak base. So this buffer contains 0.10 mole. Careful, doesn't say molar. It says just moles of NH3. And we know the second component must be the salt of this. And we know already from the previous chapters that the salt of ammonia is NH4. That's why they added 0.11 moles of ammonium chloride. Because the salt, remember the salt, all salts, again and again and again, salts The salt contains a cation and a anion. So that forms your crystal, the little crystals there. It's a solid when you dissolve down water. And we know the cation comes from a base and the anion comes from a acid. So here, why do we choose this salt? This NH4Cl. Because that salt contains the conjugate base of the base, so the conjugate acid, NH4 plus, this is Cl minus, the conjugate acid of the base we are using. Do we care about the chlorine? No, the chlorine is just a companion to balance the charges there. And we know chloride ion, Cl minus, comes from a strong hydrochloric acid, therefore Cl minus is too weak to react with water. Any salt that contains NH4 will be suitable for that. Of course, we use ammonium chloride because it's cheaper and it's easy to find and works well. So yes, we have the two components of a buffer. Now let's see what will be the pH resulting of this particular combination. First, we need to find concentration. Well, actually, I will show you that for buffers and only for buffers, you really don't need to use concentration. You can use it if you want, but you will see later that you can use moles also. Working with buffers is actually a lot simpler. It's going to simplify a lot of things, and you will see. It's easy and nice to work with buffers. All right. So in order to find the pH, of course, we need to know. So here, we know the volume. The volume of the solution is 2 liters. We can use this to find molarities. So the molarity of this will be 0.10 divided by 2. It's going to be 0.050 molar. And this also, you can find the molarity. But you will see this is no need later. You can apply into the formula just the moles. Kb is given. Kb for the weak acid is given. So the question is the pH. What is the pH? So what do you need to find the pH? Of course, we need to find concentration of H+. And we don't know that. But this is not an acid. So how do we measure concentration of H+ if this is not an acid? Well, so that means we have to find the first concentration of OH minus, or find the POH, find the POH, and from here you can find concentration of H+, or just find the pH. So we need that. So this is the procedure. And there are, let me write the two equations so you can see clearly what's going on there. the equation for the ammonia and the equation for the ammonium chloride. So the equation for the ammonia is this, and that is a dissociation. You have this amount reacting with water to form ammonium ion and OH minus. And this is the one that is going to help you to find the pOH, therefore the pOH. And this is the Kb for this equation. We found the concentrations. Actually, we are going to do it. Molar concentration, the one I just said here, moles divided by liters to give the molar concentration, 0.050 molar. And similar, we do moles of the salt over 2 liters to give 0.055 molar from the ammonium chloride. So we can plug over here. So we know, notice that we know this, and we know that. Here is the beauty of this. We don't have to make a table. I know. That's a good thing, that's a good news. Whatever the initial concentrations of reactives are given, you can plug it directly into that formula. Why? Because most of the ammonium comes directly from that dissociation of your ammonium chloride. Remember, the ammonium chloride is a salt, NH4 Cl minus is a solid. When you put down water, what's going to happen? Dissociates, breaks down into its ion, forming NH4 plus, aqueous plus Cl minus. Of course, the ionization of ammonia is going to produce some. At the equilibrium, there's going to be some of this. That's your X. You remember we did it last time? A table for the dissociation of just ammonia. Find X and X at the equilibrium. Remember, or can you predict the extent, the value of that X? Knowing that Kb for ammonia is 1.8 times 10 to the negative 5? Yes, you're right, very small number. So most of the ammonia will come from here. That's why you add it here from this. So you have a lot of ammonia plus 0.0000 basically is the same initial amount. And same thing here, very little dissociated of this. So that's why we apply the initial concentrations, and that's what we're going to do here. Put it here. We know this, we know this, we know this. Find the OH minus. So if we solve from this equation for OH minus, because that's what we want, you say concentration of OH minus equals, and let's move things around, it's going to be Kb times concentration of NH3 over concentration of NH4 plus. So the base divided by the conjugate acid times Kb. So concentration of OH minus will be Kb, which is 1.8 times 10 to the negative 5 times concentration of ammonia is this 0.050. What is molar, right? Which is mole per liter over concentration of ammonium, which is this 0.050. 55 moles per liter. So notice that on this ratio we have moles per liter over moles per liter, and it's 1 liter, right? So that's why these two cancels out. So at the end, we get just moles. That's why I was telling you at the beginning, there's no, for buffer and only for buffers, really don't need to find molar concentrations. And from here, we just realize that when you plug that, operate these numbers, you get, I think I have the answer here. You get 2.0 times 10 to the negative 5, that's the PO, the concentration of OH minus. Then you find the POH, which is 4.70, and pH plus POH equals 14. Therefore, pH equals 14 minus POH, which is 9.30. Done. You see how simple is that? Just using the definition of KB. Similar when we do the for weak acids. So instead of weak acid, for weak acid we use Ka instead. And that's it. That's how you work a buffer. Again, summary. You use the equilibrium expression for the weak base or the weak acid, depending on what you have. Initial amount of this is given, so you can put it here. It could be molar concentration or just moles. Initial concentration of the base is given. It could be molar or just moles. Sulfur OH minus. And that's it. Find the pH or POH. There's a little modification on this formula that we just created here. From here, remember we were solving for OH, concentration of OH minus equals Kb times concentration of, let's put in general, concentration of the base over concentration of the conjugate acid. So that will be HB minus in general. Oh, sorry, plus H, because we are adding the H. HB plus, this is the conjugate acid of the base. In general, for any base, look, a simple formula. What about you have a acidic buffer? So for acidic buffer, you will find concentration of H plus, which is going to be equals to what? Guess what? What did you say? Yes. Ka times. Don't need to look anywhere else. Just look at here. So what's going to be here? Yes. Concentration of the acid over what? Concentration of what? Of the conjugate base, which is A minus. Bingo, we did it. That's how you calculate the pH or POH of a buffer. This is for a basic buffer and this is for a acidic buffer. Most of the times you want to know pH, not POH. So from here you find POH and from here you find pH. You need to do this extra step to get the pH. There's a mathematical treatment to these equations, and we can choose this one, for example. If we take negative log on both sides, we are going to get something really interesting. Look, what is negative log of concentration of H plus? This is right here, taking negative log on both sides of the equation. Of course, has to be on both sides. So negative log of concentration of H plus, what is that? What is negative log of concentration of H plus? Yes, it's pH. So negative log of this is going to be pH. What is negative log of Ka? Yes, pKa. This is a product. When you take negative log of product, is going to be negative log of the first term plus negative log of the second term. So negative log of the second term is going to be negative log of concentration of HA. And remember, those are initial concentration, don't need to be equilibrium. I explained already why. Why we can do that exception on buffers only. All other problems with weak acids and weak bases, we need to do the ice table and find the equilibrium concentration. So we did last time over the salt. But remember, we can change this sign for plus. If we were to change this sign for plus there, then those two will switch, will swap. So leaving pH equals pKa. Those are properties of logs. I recommend you at the beginning to study, to refresh your memory. Plus log of what? Concentration of the salt over the acid. This beautiful equation is the famous, useful buffer equation to find the pH. And that will help you to make the calculations to prepare any buffer you want, any buffer solution you need. And this is called the Henderson-Hasselbalch equation. This is the famous Henderson-Hasselbalch equation for buffers. And I show you where this comes from. Or you can just work with this. You don't have to use this. Did you remember this is easy because you know the pKa's. You know the pKa's, and also interesting application of this. It helps in many ways to prepare buffer solutions. One, it helps you to choose the right acid to prepare a solution with the buffer you want. For any buffer, we always want to have this ratio close to 1. The ratio between the salt and the acid can be close to 1. So let's say if concentration of A minus over concentration of HA is close to 1, or equal to 1, then so that means this concentration is very close to this, so this becomes 1. So then the log of 1 is 0. So this expression, if this is true here, this expression will become 0, right? Because log of 1 equals 0. And you ended up with pH equals pKa. And that is great, because then in a list of weak acids or weak bases, we choose the weak acid that has the closest pH to the pH we want or we need. I'll show you a list of some of those weak acids and weak bases. All right, so this is what we did before, and this is the famous Henderson-Hasselbalch equation. That's the one I showed you. Positive, the salt is on top and the acid is on the bottom. And useful buffer, the pH should not change in more than 1 unit around the pKa. So that means the pH should not change in more than 0.1 units to stay stable and to work as buffer. Of course, if you add too much of the strong acid or too much of the strong base to that buffer, you will break the buffer's capacity, so the buffer will not work anymore. We cannot get too crazy adding extra strong acids, strong bases to the buffer. You will break, you will damage the buffer. That's not going to work anymore. You need to prepare a fresh buffer. So it will accept a fair amount of extra acids or bases. However, the pH should not change more than 0.1 units. Let's see this one, this problem. This is a buffer made from 0.10 molar acid, HA represents the acid, and the pKa of the acid is given, 7.20. You see how useful it is to work with pKa's instead of working with Ka's? And 0.15 moles of NaA, that's the salt, containing the conjugate base of the weak acid HA in 2 liters. And somebody added 0.02 moles of hydrochloric acid, strong acid, assuming there's no change on the volume, so the concentrations don't change. What is the net ionic equation for the reaction when the HCl is added to the buffer? And what is the pH change? And also we are going to see what will happen when you add the same amount of HCl, 0.02 moles of HCl into pure water, into 2 liters. This is 2 liters of pure water. Just for comparison. So the first thing is to find the pH of the original buffer. Before the addition of hydrochloric acid, we use Henderson-Hasselbalch equation to find the pH of the buffer before we add the hydrochloric acid. So pH equals pKa, which is 7.20 is given, plus log of the salt over the acid. And those are the initial, notice that we are using the initial amounts in moles. We didn't have to calculate the molar concentration. And the pH, 7.38. You see how easy is that? 1, 2, 3. 1, 2, 3. We just found the pH of the buffer using the marvelous Henderson-Hasselbalch equation. Now let's see the changes. Once you add the changes that occur in the solution, once you add the extra hydrochloric acid, and how that is going to affect the pH. So let's see what happened with the concentrations. Hydrochloric acid is a strong acid. Let me write it here so you will see it better. Remember hydrochloric acid, HCl, aqueous, plus water, liquid. It's a strong acid, goes only one way to form H3 O plus, aqueous plus, Cl minus. So it's very strong. Who's going to be affected? The first one, remember on the previous example, what species, the salt or the acid, will come to counterattack the addition of acids? And we said the conjugate salt. Because this is negative and really want protons. If you provide those protons, it's going to react with this right away. And that is going to come from the addition of hydrochloric acid. So how much of this was added? This extra 0.02, I believe. 0.02 moles of hydrochloric acid. So 0.02 moles is added. What's going to happen? It's going to react HCl plus your conjugate base with this one, whatever you have there from the salt. Completely. This is a strong acid and it's going to react completely. So you have 0.02 moles of that, will use 0.02 moles of the base to form the acid plus Cl minus. So this is going to use some of the salt. By how much? It's going to take that much. The stoichiometric proportion is 1:1. So that's why we subtract the initial minus whatever is taken from that initial to react with the acid, and at the end we have the final concentration of A minus. And how the concentration of HA is going to modify, it's going to change. It's going to change because the same reaction is making HA, the acid. By how much? 0.02, because this is a strong reaction. It goes all the way down. So it's going to add. acid. Initial plus whatever comes from here. So the concentration of A minus goes down and the concentration of the acid goes up. Now we have the new concentrations, we can find the new pH. 7 using the Hasenbach equation, plug over here the salt over the acid and you get pH 7.23. What was the pH change compared to the previous one before us adding the acid? So the difference is just 0.15. So the pH went up. Oh, sorry, went down to 7.23 because the pH of the buffer was 7.38. Yeah, 7.38 before the addition of the acid. Once we add the acid, the pH went down a little bit, so the change was 0.15, which is great. Basically, very little change on the pH of the buffer after you add that many moles of strong acid. Let's see what will happen, and this is just addition to the problem. What will happen if we had 2 liters? This is a 2-liter solution of buffer. Let's assume we have 2 liters of just pure water. What will happen, and the pH here is what? pH is 7. What will happen if we add, by mistake, 0.2 moles of HCl? What will happen with the pH? Well, let's find the concentration. So the concentration of H plus from here will be the initial amount, 0.2. Remember, this is a strong acid and ionizes completely. So the Killian concentration of H3 plus is going to be 0.02. That's why I'm using here the same number. Moles over 2 liters. So the concentration is 0.0 0.2 0.01 molar. That is 1.0 times 10 to the negative 2. So what will be the pH of solution containing that amount, that concentration of H plus? So pH will be negative log of the concentration of H plus, which is 1.0 times 10 to the negative 2. What is the pH of this? 2. Look, if you have 2 liters of water and add 0.2 moles of hydrochloric acid, the pH goes from 7 to 2. Wow. It's a huge pH change. If you have living cells there adjusted to that pH, and you add this, you will kill all of them. All of them. Or you destroy your solution. If you have proteins there, the proteins will come to denaturalize. Denaturalization of proteins by changing the pH. That's how you kill your cells. Your cells will become like a fried eggs. That's what happened when, of course, denaturalization of tertiary proteins, secondary proteins, or primary proteins. Just by changing the pH. All right, so you see the beauty of this equation? look at this problem. Which one of the following is a buffer solution? So we need to check every combination to see if every combination fulfills the requirement for a buffer solution. Let's see. Let's analyze. First one. We don't care about the numbers, but we want to look if we have the right components. Remember, the buffer solution is made of weak acid and the conjugate base of the weak acid. Or, conversely, a weak base and the conjugated acid of the weak base. Let's say that fulfills here. What is this? Weak acid. What is this? A salt containing the salt of the weak acid. Yes, it's a buffer. This one. This is a weak acid solution. Is a buffer? No, something is missing. In order to be a buffer, it will have a salt, like for example, sodium acetate. That will make a buffer. So right now, it's not. It's not a buffer. This is missing. This one, HNO3, it's an acid. And this is a salt containing the conjugate base. What do you say? Is this a buffer? No. Why not? Because this is not a weak acid. This is a strong acid, and the requirement says it has to be a weak acid or weak base. So, no. What about this? What is this? It's a salt containing a conjugate base. No. Something is missing. It's missing what? The acid of this conjugate base. Which one is this? We just learned it here. The same one. Hydrocyanic acid. So now, this one is missing. What about this one? We have an acid and we have the salt of the acid. Is this a buffer? And you may say yes, but no, it's not. Why not? Because this is a strong acid. So this strong acids, strong bases cannot work as buffers. They will not work as buffers. So no. You see the analysis? Critical thinking. All right. This is the cheating slide. You can go back and forth and review your notes. All right, so I give you more examples here for you to practice. I don't want to be that selfish. I would like to do all this, but no, I'm restraining myself. I say, like, let them do it. You can have fun solving these problems, and also I think the solutions are there, and you can come and compare your results. So yes, I put a few examples here. You can play with those. Answers are there. Come and solve it and then compare. Don't cheat. Don't look at the answer first. Try yourself and then compare to the values. Also, on the Blackboard, I attach a document that uses solving problems using Henderson-Hasselbalch equation. It's a nice document that shows different type of problems, and they are solved step by step, explaining in detail how to use the Henderson-Hasselbalch equation to solve different situations of acids and bases, of buffers. So I recommend you that document, go through it, solve the problems. Let's see what is new here. Same thing, it's just more problems to practice, buffers. Polyprotic acid, we did that already in the previous video, so we don't have to spend here. We did this, I explained this step by step. We actually solved one problem, titration. This is new, and I want to spend time on this one, on titrations. All right, what is a titration in chemistry? Titration is technique used in chemistry. It's technique used by chemists. Very useful technique. And since we are working with acids and bases, I'm going to show you how to do acid-base titrations. There are different types of titrations. Gravimetric titration, also redox titrations, but now we are going to focus only on acid-base titrations. What is that? What is that technique? All right. Let me explain here. Since I didn't write specifically the definition of titration. I want to put it here. So in this technique, you will need to use, this is an awful drawing. Now, let me do something different. This time, what I want to do, yes. See? Oh, look at that. Yes. It's beautiful. I think I'm drawing better now. You see, the practice makes perfection. So this instrument is something like this. Oh, okay. Here. Do you know the name of this glassware? Lab glassware? Yes, this is called the burette. Very precise instrument. You were using this last time in Chem 11. You saw the demonstration, Chem 11, titration. And you were actually doing calibration also of burette. You see how precise is this? Usually goes, has a mark here and a mark here. This is your zero volume to start with. You start with zero volume and then you start dispensing, and the burettes we use in the lab are 50 mLs, 50.00. So this is 0.00 to hundreds of ml. That's the precision. Of ml. So in this technique, we use this instrument called burette. And here we add a base. The characteristic of this base is that you know exactly the concentration of the base. It's known. You know that. Very precisely. Usually standardized. They are standardized concentration. So that means we know for sure what is the exact concentration of the base, and that's the one goes here. On the bottom here, we use another instrument that has this shape. In other parts of the world, they call it conical flask. Here we call it, has a funny name. And you remember the name of this? Erlenmeyer flask. What goes here? Over here, we add the acid. Characteristic of this addition here is that you know the exact volume to the highest precision. So let's say usually it's 10 mLs, 25 mLs, using volumetric pipette. So you know the volume precisely. What about the concentration of the acid? Do you know the concentration of the acid there? That's the problem. We don't know. It's unknown. And that's the purpose of this whole process, of this technique. So this technique consists on a acid-base neutralization to find a unknown concentration of one of the components. And that's how we find the concentration of my unknown. We have a solution in the lab. We don't know what is the concentration. How do you find the concentration of the solution? Using a titration. Now we are going to use acid-base titration because we are going to use using only acids and bases. Again, most of the times, the base is going to be here and the acid is going to be here. It's not mandatory to do it in that order. You can, in some other cases, you can put the base here and the acid here, but what we want to make sure is that whatever you put in the burette, you know exactly the concentration, the exact concentration of whatever you put here in the burette. So it's easier that way. Some people actually do it the opposite, but I think it's a lot easier and more convenient. If we prepare the right solution, a standardized solution to make increments that will reflect the concentration, that will be very easy to find the new concentrations. So once we finish the titration, and let's not forget something else. Here we add a very specific value using the volumetric pipette. So we know the volume. Later, you can dilute this. If you add 25 mLs of the acid, you can dilute it up to 100 mLs, for example. That's what you did in your Chem 11 titration. You actually dilute it to use less of my reactive. So this is going to be, whatever goes here is going to be your titrant. And whatever is here and now is going to be your analyte. You want to find the concentration of the analyte using a titrant with known concentration. And you add the acid in this case, the base to the acid until you neutralize the solution. So we have acid, base, neutralization. Acid-base neutralization there. But how do you know when your acid is being neutralized? Don't we have something missing? How do you know? You add the base here to neutralize and keep adding and keep adding. How do you know when to stop? Do you remember what you did? What did you do? Yes, you must add a acid base indicator. For this particular case, works very well when we have the acid here, phenolphthalein. Remember, the phenolphthalein changes, is colorless up to 8.2 pH, and then it's pink about 8.2. Pink, and here colorless. So that's how you prepare everything there. You don't forget to add two drops of your indicator. Since this is acidic, it's going to be colorless. So you start the titration very slowly until you get the end point of titration. So you add until you find the end point of titration. Who gives you the end point? Who gives you the signal? Stop. Who gives you the color change of the indicator? And that's why you need to choose the right indicator depending on what titration you're doing. I showed you last time a table with many different types of indicators, everyone possibly changing in different pH ranges. So we need to choose the right one depending on the end point of your neutralization, the equivalent point of your neutralization. And you have to be aware of what indicator you are using and what's the color you are expecting on the acid media or base media, and the color of the transition. Sometimes the color of the transition is different when the indicator is on acidic or basic, because you will have a mixture of colors there. So that's basically titration. And what we want to achieve here, we want to achieve acid-base neutralization. And what is that? What is the acid-base neutralization? So we have an acid reacting with the base to form what? Salt and water. That's the neutralization reaction. And what is the net ionic equation for a acid-base neutralization? H plus from the acid plus OH minus from the base to form water. This is what we call the net ionic equation. So at the equivalent point for the neutralization, and we say neutralize number of moles of acid is exactly the same number of moles of the base. Yeah. Number of moles of the acid equals number of moles of the base, and that's what we call neutralization. And this is called the equivalent point of the neutralization. So the equivalent point is exactly when the number of moles of the acid equals number of moles of the base, and that's the neutralization. The acid has been neutralized by the base. Or you can say the base has been neutralized completely by the acid. What happens if you keep adding acid to the equivalent point, after the equivalent point? Well, now the solution will become acidic. What about if we keep adding base after equivalent point? Then your solution, the final solution, will become basic. The equivalent point, also the pH at the equivalent point depends on the nature of the acid and base you are combining. So we have to be careful with that, because if we are neutralizing the weak acids or weak bases, or we have both of them, then they will also, at the equivalent point, have some salts of the acid or salts of the base, and that will behave as buffer. And those salts, remember, those salts of the weak acids or salts of the weak base are strong enough to react with water, and they will produce a secondary reaction right there at the equivalent point, and will change the pH at the equivalent point, at the neutralization point. So the pH at the equivalent point is not always 7, because it depends on the nature of the acids that are reacting, or the base that are reacting. I'll show you a couple of examples. So we want, during this technique, we want to be very precise to reach this point. But this is happening at molecular level. We cannot see if the acid has been stoichiometrically neutralized by the acid. We cannot see molecules to say stop. However, that's why we add the indicator. And we need to choose the right indicator that gives the color change at the equivalent point, or close to the equivalent point. At the beginning, probably you miss the color change, so you miss the equivalent point, but that's fine. That will introduce some error. But that's why you do it 2 or 3 times. You do the titration 2 or 3 times. 5 is even better. So after you practice doing that neutralization, you educate your eyes to detect very quickly the color change, and also you educate your hand, your fine muscles on your hand, to stop the neutralization, to stop the stopcock here. So your eyes see the color change, complete color change, and your hands close the valve right away. See, it's just training to get close to the equivalent point, to the neutralization point. Once you get this, now you can do calculations, because then you will find exactly the volume used by the titrant. Volume of the titrant is well known. You subtract, this is the initial volume, this is the final volume, so the volume of the titrant will be final volume minus initial volume. Remember, you count from top to bottom. This is your 0, you measure the mLs from top to bottom, not from bottom to top. I have seen many people counting or measuring the liters from bottom to top, which is wrong. So you find the delta volume there. So that's well known. So you know the volume of the base, and you know the concentration of the base. And that will give you the moles of the base. What is moles of the base? Moles of the base equals molarity of the base times volume of the base. And that should be equal exactly to the moles of the acid. And what is the moles of the acid? We know the volume precisely, the volume of the acid precisely, but we don't know the concentration. We know the volume, but we don't know the concentration, the molarity. Sorry, we don't know that. That's unknown. So what is the moles of the acid? Moles of the acid equals molarity of the acid times volume of the acid. So we are looking for the molarity of the acid because that's the purpose of the whole titration, to find the concentration and non-concentration. So from there, molarity of the acid equals molarity of the base times volume of the base over volume of the acid. And that's it. And that's how you find it. Also, you have to be careful with the stoichiometry of your reaction. If you have diprotic acid, you have different bases, you have to be taking that into account, the mole ratio on your reaction. So let me give you a couple of examples. This should be the graph for a titration of a strong acid and strong base. Graphing pH against volume of the base added. So remember, we know exactly what is the concentration. The initial, since we are titrating strong acid against a strong base, usually also you can use two different ways to do it. The old technique using the color change, the indicator, or nowadays we use a pH meter, an analytical instrument. You put a probe here with the pH meter, so that's going to be a potentiometric titration. And what you need to do is just follow the pH changes, and you know where the pH is going to, what pH is going to indicate the equivalent point. So you need to know exactly what is the pH of that for the neutralization. So we can graph a pH against volume, and you will get something like this. The initial pH, here is the initial pH, since we have a strong acid, and the strong acid here we have HCl, 0.2 molar. So what is the pH of 0.2 molar hydrochloric acid? So the pH, initial pH, before you start the titration, the pH will be negative log of the initial concentration of hydrochloric acid, which is 0.2, and the pH, how much is that? 1 point something, right? So you have 0.2, oh, 0.69. Okay, 0.69. And that's what you have there. Initial pH here, you see, 0.69. That's the pH initial. So just start the titration there. Then you start adding the base, adding the base, adding the base very slowly, and look at the curve starts to go up. The pH starts to go up. Initially it takes some time, and you are adding more base until you get this flat line up at exactly, when you add exactly 25 mLs, because here the ratio, the stoichiometric ratio is 1:1. HCl plus NaOH, the ratio H2O plus NaCl. The ratio is 1:1. And you are using exactly the same concentration. And you have 25 mLs of the acid, so it makes sense that you will need exactly 25 mLs of the base is with exactly the same concentration to neutralize that, because it's 1:1. 1 mole neutralizes 1 mole, and 0.2 molar will neutralize 0.200 molars if you have exactly the same value, like we do here. So you will see this flat line, vertical line, and then you reach the equivalent point here exactly at pH 7. Because sodium chloride is being formed, and this is a neutral salt, will not change the pH of the water, and the pH of this neutral salt is 7, and you put in a water. Only when you are using these two acids and bases strong. And right here, about the halfway up on this straight line is where you get the pH at the equivalent point. That means at this pH, number of moles of the acid equals number of moles of the base. But the curve, the graph can be changed if we are using different combinations, and that's what you are going to do in the lab. In the lab, you will have you will see different titrations, a demonstration about different titrations, different strength, combination of strength of acids and bases, and you will see different shapes on the graph. Also, the initial concentrations, initial pH are going to be different, and you will notice the pH at the equivalent point is going to be different. It's not going to be always 7. So let's see this one. I'll do this one, and then I'll let you do the rest, because they are all similar. It's the same, exactly the same analysis when you do titration. Here, we have a solution where we mix. I like to draw diagrams to show exactly what we have. So we have one solution here, and this solution is 100 mL of HCl, and we know this is HCl, aqueous, and we know the pH of this solution is 3.00. And we have another solution containing 50 mLs, in this case KOH, and the POH is 6. So the question is, if you put those two together, you mix these two in a new container, in another container, what is the pH of that new solution? Obviously, the volume for the final solution is going to be what? 100 mLs plus 50 ml. So the volume of the final solution is going to be 150.00 mLs. But we need to find the pH. So what's going to happen here? You are adding acid and base. It's going to be acid-base neutralization. At some point, one of these is going to neutralize the other. Exactly. Because we have the reaction here is going to be HCl, aqueous, plus KOH, aqueous, to form H2O plus the salt, KCl. Aqueous. This is liquid, and this is aqueous. So here we have 1-to-1 ratio. At some point, one of those, the limiting reactive, is going to neutralize exactly the other one. And since one of them is in excess, that excess is the one that is going to give the pH of the solution. Because remember, this salt is neutral. Also, you notice that this is strong and strong. So we have a strong acid-base reaction. Strong acid, strong base. And the stoichiometry is 1-to-1, according with the equation. One of them, the limiting reactive, is going to neutralize a portion of the reactive that is in excess. And whatever is left over of that reactive that is in excess, that is what is going to give the final pH of the solution. So let's find these numbers. Here we know the pH. What can we do? What can we do with the pH? Remember, we need, from here, we really need to know exactly what is the concentration of H+. And here, what we really need to know is the concentration of OH-. We can find that. So if the pH is 3.00, how do we find the concentration of H+? Yes, 10 to the negative pH. So that's going to be, if you plug that into your calculator, it's going to be 10 elevated to negative 3.00. So the concentration of H+ on the first flask is going to be 3.00, and we do 10 to the x. Do I have something wrong? Probably, I'm not using this. What is the pH? Oh, pH 3. Oh, okay. Yeah, you see, I missed something there, and that's why we get the crazy number. It's 10 to the negative, right? pH is 3. I didn't hit this button. Now 10 to the x. There you go, that makes sense. 0.011 times 10 to negative 3. You should know that from the beginning. All right, just to practice how to use the calculator. So this one concentration is 1.0 times 10 to negative 3. That's the concentration of H plus and flask number 1. This is flask number 1. Now in flask number 2, we want to know also what is the concentration of H plus, but we don't have H plus, we have OH. So let's find that first. How do you find the concentration of OH minus? Similar. Concentration of OH minus, if we know the POH equals 10 to the negative POH, which is 10 to the negative 6. So it's going to be 1 times 10 to the negative 1.0 times 10 to the negative 6. That's the concentration of OH minus. But we don't want to know the concentration of OH minus. And we don't even want to know what is the pH of that solution. We want to know is what is the concentration of H plus. And you remember one of the equations we learned on the previous video is that concentration of H plus for any given solution equals 1.0 times 10 to the negative 14 divided by concentration of OH minus. So it's going to be 1.0 times 10 to the negative 14 divided by 1.0 times 10 to the negative 6. And that gives you 1.0 times 10 to the negative, so you subtract these two. So it's going to be negative 14 plus 6. It's going to be to the negative 8. That will be the concentration of H plus. And that makes sense because that is a basic solution. But we don't want to know what the pH. We just want to know the concentration of H plus. Here, before you add. Now we can see the stoichiometry over there. Oh, hold on. I jumped one of the steps. I just realized we really don't have to do this because we didn't do the neutralization. I was mentioning the limiting reactive, we neutralize the other one. So let's do that. I was thinking ahead of this for the final results, and we really don't. But first, we need to do the neutralization, all right? When you put them together, we already know what is the concentration of OH minus, so we can do the neutralization now. So those are moles per liter. Now let's find number of moles. Number of moles of OH minus and number of moles of H plus here. How do you find number of moles? So number of moles of H plus, from the definition of molarity, molarity equals moles over volume. So number of moles equals molarity times volume. That's what I'm going to use here. So number of moles of H plus equals molarity, which is 1.0 times 10 to the negative 3 times the volume. And what is the volume here? 100 mLs. But remember, we need to use liters. So there's going to be 0.100 liters, 0.1. So number of moles of H plus equals 1.0 times 10 to the negative 4. Let's find number of moles of OH minus here. Number of moles of OH minus equals 17. Molarity times volume. And the molarity is 1.0 times 10 to the negative 6 times volume, which is 50 mLs. That is 0.050. So the concentration here is 1 times 10 to the negative 6 times 0.05, and you get 5 times 10 to the negative 8. 5 times 10 to the negative 8. That makes sense. 5.0 times 10 to the negative 8. That's the concentration of NOH. So remember, we are doing this because we need to neutralize. These two are going to neutralize. When they come in contact here, they are going to neutralize each other. Which one is going to neutralize to who? With the acid-base neutralization, acid plus base forms salt and water. So we know the exact concentration of the acid here, number of moles. You need to work in moles. That's why it's important to know what volume is in every container. So the moles here of the acid is 1.0 times 10 to the negative 4. I'm writing it here so you can visualize what's going to happen. 0.00 times 10 to the negative 8. So which one is the limiting reactive and which one is in excess? Which one is in a small amount and which one is on the large amount? So notice that this is in a small amount compared to this small number of moles. So the base is going to neutralize the acid with this number. So that means, and since the neutralization is 1-to-1, it's easy to think that after neutralization, what is left over? Acid, because you have more acid than base. Or you can use stoichiometry, conversion factors. So you feel comfortable using conversion factors, you want to know how many moles of acid you will have after neutralization. But here, just by looking this, you will notice that at the end, you will have moles of acid in excess. All this will go. So the acid, moles of the acid in excess will be 1.0 times 10 to the negative 4 minus 5.0 times 10 to the negative 8. And that will be 1.0 times 10 to the negative 4 minus 5.0 times 10 to the negative 8 equals 9.91, basically 1 times 10 to the negative 5, rounded off. 1.00 times 10 to the negative 5. That will be left over of acid after the base neutralizes the acid, because the base is in less amount. So you need to check which one is in bigger amount, which one is in the small amount, to see what is going to be left over. In this case, this is, we have more of this than that, so this is going to be left over, and the difference will show you how much is left over. So that will be concentration of H plus after neutralization, or left over. So that means that's the one that's going to give the final. Here, once they combined, the new concentration of H plus is 1.0 times 10 to the negative 5. Oh, sorry, no, this is no concentration. I got so excited. Not yet. This is no concentration. This is just moles. The number is moles of acid in excess. So we need to find the concentration. Now let's convert back to concentration. So concentration of H plus equals molar concentration, right? So that's molarity. Equals moles over liters. The moles is 1.0 times 10 to the negative 5 divided by the volume. Well, the volume now, the total volume now is 150 mLs. In liters, that's 0.150 liters. So this is moles, this is liters. And when we do that, divided by 0.150 equals 6.7 times 10 to the negative 4. 6.7 times 10 to the negative 4. I didn't round off this number during the calculation, so we don't carry errors. That's why I got that number. So that's the concentration of H, final concentration of H plus after neutralization. Now we can find the pH. pH equals negative log of that number of 6.7 times 10 to the negative 4. What is that? Remember, don't wait until I do it here. You stop the recording and do it yourself. That's how you practice and gain the speed for the exam. You don't get the speed, you don't gain the speed and the skill. You will take forever solving one of these problems during the test. I'm here spending more time because I'm explaining every possible situation. All right, so let's find the pH. So let me show you again. 6.7 times 10 to the negative 4, right? So we write 6.7 exponent -4. And we take the log of that. And that's going to give a negative number, but since we have a negative log, it will change. It's going to be 3.17. 3.17 is the pH. So we have 3.17. That's the answer. So that's how you do the analysis. When you're working with acids and bases, see which one is neutralizing, measure number of moles, take into account the values to find new concentrations, etc. I did a complete analysis here, and you can apply this analysis to solve any acid-base neutralization process or titration. I'm going to leave here. I'm going to give you some extra problems here for you to practice. And the next time, I'll show you a couple shapes of titrations. We'll continue with the rest of this chapter. All right.